we'll start by introducing our seminar speaker today.
Great to have Professor Smita Mathur, who is a professor at the Department of Astronomy at Ohio State University. Prior to joining the Ohio State University in 1999, she worked as an astrophysicist in the High Energy Astrophysics Division at the CFA Harvard and earned her PhD at the Mathur Institute of Fundamental Research in India. Her thesis title actually is Effect of the Quasi-Stellar Object on its host galaxy. And Smita is renowned for her expertise in observational study of the circumgalactic medium and intergalactic medium, AGN physics, X-ray astronomy. Just makes significant contribution to the study of AGN, exploring the role in the cosmic energy budget and the impact to the surrounding environment. Work on X-ray and UV absorption line has provided some of the earliest evidence for the existence of the warm-hot intergalactic medium. So it's really great to have her here. And today talking to us about circumgalactic medium, but I'm sure you guys can ask many questions because she's so friendly. So please do take the opportunity.
We're really thrilled to have her here today. And so
we're looking forward for the insight that's about circumgalactic medium today. And please join me in welcoming speaker. And over to you.
Thank you.
Well, thank you so much for having me here, and thanks for that great invitation, great introduction. I should have you write my letters for me or something, because as she was speaking, I was like, oh, wow, really? So that's great. Okay, thank you. Yeah, so I'm really excited to talk about the work we have been doing on the warm hot circumgalactic medium, or CGM in short. And so because, and I'll define what is warm hot, what exactly is CGM in just a bit, but this work is mostly done in X-ray astronomy. So this is what you see here is the great observatories, Chandra, which is a NASA mission, and XMM-Newton, which is a European mission. And not much appreciated and talked about is this little X-ray telescope called Suzaku, which is a Japanese mission, which actually gave us a lot of good data that we have really worked on. So that's, I'll be basically talking about work done with data from these missions. And these are my collaborators, few of them are listed here. My longtime collaborator, Yair Krongold from UNAM, Mexico, my former postdoc, now colleague, Anjali Gupta, and my amazing graduate student, Sanskriti Das, who I miss so much because now she has graduated and gone away as a HIPAC fellow to Stanford. So let's talk. Okay, now what works? Let's see, how do I go forward here? That doesn't work. That doesn't work. That doesn't work. Let's see what works. That works. Okay. So since most of you, I guess, don't do this for living, so just a little bit of a background as about our universe. What is our universe made of? We all know that good 73% of it is dark energy. Whether it is really energy or is it modification to GR, we don't really know, but there is reasonably good evidence that something is happening which is accelerating the universe. Though some people would question that also, but we definitely know the existence of other 23%, which is the dark matter. We 100% know that, flat rotation curve of galaxies. Nothing more is needed to convince us its existence, but we have absolutely no idea what that is made up of. Okay, so that leaves us with just 4% of things that we really know and love, the normal baryonic matter, but that also is kind of missing in the low redshift universe. We know how much of it is there because we actually see it in the high redshift universe through Lyman alpha forest. But as you come to low redshift, much of that baryonic matter also seems to be not there in Lyman alpha forest. It thins out. And so what you actually see that in the low redshift universe, baryonic matter is missing on all scales. If you consider the largest scale universe totally, then we see that the baryonic to dark matter ratio is way smaller than that of the cosmic average. And if you now come to smaller scales, on the scales of galaxies, you again see that the baryonic to dark matter ratio is not cosmic. It's only in clusters, and that too relaxed clusters of galaxies, which are really massive, that the ratio appears to be close to the cosmological average. This is what I'm not going to talk about. That is the intergalactic medium, where the baryons seem to be hiding, that we don't have observational capability to really constrain it very well at this stage, but next generations of telescope would do that. So what I'm going to be talking about today is this parameter space. I'm talking about galaxies, and one of the results that we have is that the so-called missing baryons appear to be in the circumgalactic medium of around the stellar disks of galaxies. So that just to motivate you about what why it is important, but really even on a different scale, understanding CGM is really important to understand galaxy formation and evolution. Is the lighting okay, or should we need to dim it? If it's okay for you, it's okay for me. Yeah, okay, I think that's a little better, right? Yeah, so what you are seeing here are from the simulations of galaxy formation simulation, you see that the material is falling in, and you will see as the time goes on, there are mergers happening, and the stellar disk is getting formed, and this is on more larger scale. You can see some other halos coming in. Here you can again see the stellar disk is forming, but the main takeout from these simulations that I would like you to have is that as the galaxy is forming, it's not a very efficient process in that all the gas is not making stars. A lot of gas you actually see is outside of the stellar disk, and that gas is what we call the circumgalactic medium. So that's the definition of the circumgalactic medium, is the gaseous, the halo of a galaxy that's filled with this gaseous component we call the circumgalactic medium. And the process of galaxy formation actually shock hits this gas to very high temperatures. So that's what the warm hot part comes in. As much fun as it may be to see the movie, I think I'm going to stop it here, and so that we can continue our discussion. These are again some just a snapshot, some different kind of simulations here, showing you that the gas is distributed on hundreds of kiloparsec scale around the stellar disk of galaxy, how much far out it is, and what its properties are depend on what, the mode of feedback. This panel is for low feedback, this is for high feedback. And what I mean by feedback is the interaction of the stellar disk of the galaxy and the surrounding medium, be the feedback, be the energy momentum transferred from the nuclear AGN or from the star formation related activity, which would also expel metals into the circumgalactic medium. All of these things contribute to the properties of the circumgalactic medium, which is why in totality, understanding the circumgalactic medium is really important to understand galaxy formation evolution. That's the point I'm trying to make here, as the whole CGM is sitting at the nexus of the stellar disk on the one hand, and the intergalactic medium on the much larger scale. And as I said, the gas is not showing. No, no. Why is it not changing? Now this is showing. This is not showing. Sorry?
The internet match.
Oh,
Is it slides changing over?
yeah, they are changing on mine. Oh, so now the slides are all gone. So let's share it again. Yeah.
Maybe we have to change it to presentation.
It was in the
Yeah,
presentation
I
mode.
think it's just a clash.
Yeah. Yeah. Okay.
Hello, everyone online. Hi, can you guys hear us? Okay, sorry that we
Yes.
have. Okay, perfect. Thanks. Okay, cool.
Do I have to join again? I'm wondering what's happening.
so.
I think so.
And do you mind just
Yeah.
we have the link?
Yeah, let's restart it. Yeah.
Sorry, we're just having some technical.
Problem, and we'll soon get back. And we can have a signing share.
No, but I'm here. I'm on Zoom.
Yes, I
So
think we just need to
just need to do this.
do
Yeah.
the
I don't need to join the. Yeah. Okay. I think this is where we had left. And let's try again. Yay, Eureka. Okay, all right. So, where was I? So what we were saying is that I kind of mentioned that in the process of galaxy formation, the CGM gets shock heated to high temperatures. And that's basically what is shown here is that, this temperature range here, this is over a million degrees. That's the color you are seeing here. And, this is very diffuse, very low density gas, which is at high temperature. Again, just to show you, that's what we are talking about here. So what we want to look at is very diffuse gas at high temperature, which is a difficult thing to do. So now in astronomy, 10,000 degrees Kelvin is was always reserved for warm gas. That's typically the photoionized gas that you see in the universe. Then clusters of galaxies have temperatures of 10 million degrees or more. So the hot was for that component. And so the in-between range, which is factor of 100 in temperature, between 10 to the power 5 and 10 to the power 7 Kelvin, is very creatively called warm hot. So if you ever wondered what that warm hot region is, this is where the thing comes from. I didn't call it, I didn't name it. So I'm good with that. I just use that terminology. All right. And so that's what warm hot is. So we would want to find this warm hot diffuse gas from the CGM And how do we go about detecting it, right? It's really too diffuse to emit continuum. As I said, hydrogen is fully ionized. That's why we don't see it in laminar absorption. But what we can make use of is other metals which are very highly ionized. And here by metals, I mean astronomy metals, not chemistry metals. So everything other than hydrogen, helium. Okay, so oxygen is a metal for me, and which is one of the most abundant elements in the universe. And therefore, what we could actually be looking for are the highly ionized states of oxygen, which has maybe 1 electron left or 2 electron left. That's what we mean by hydrogen-like or helium-like states of oxygen. And they are called oxygen 7 and 8, respectively. So those are the kind of ions that we should be looking for. And so this kind of science now we could do with the launch of Chandrayaan XMM. The why X-ray astronomy is important is because the major transitions of oxygen 7 and 8 have these values, okay? 21.602 angstrom, like, you know, it's only after the gratings on Chandrayaan and XMM we actually started talking about wavelengths doing X-ray astronomy, and we are not talking about KeV necessarily, okay? That's because we actually have gratings on board on these machines. That's absolutely wonderful. So this is the X-ray advantage, and that's why doing this work with Chandra and XMM have contributed so much to this work, okay? So Chandrayaan XMM got launched in 1999. And so the first decade, you know, wherever we got very good high signal to noise spectra along any extragalactic satellite, we started seeing the oxygen 7 absorption line features. Okay, so this is the background continuum, quasar continuum. You see the absorption line from oxygen 7. Look at the wavelength, 21.602, as exactly as laboratory would tell you. There is some possible indication here in this sight line, little bit of oxygen 8 absorption. For oxygen 7, not only we saw K alpha line, but we could also see the K beta line. And so, you know, you could actually, this was exciting. Like, you know, this is what you expect from the warm hot CGM. So the first decade kind of like, you know, oh, look, we see warm hot gas in this sight line. Oh, look, we see it in this sight line. But we couldn't really tell whether it is truly from the CGM, because when we are doing absorption line spectroscopy, we are measuring column density. We don't know individually what the density of the gas is, where it, what is the path length of absorption from the at redshift 0 is. It could be right in front of my nose, or it could be somewhere far away. So this degeneracy existed. We could figure out some things about the properties of the gas that we are detecting, but not really all. Okay, so this is like first decade went a lot like this, but let's remind ourselves that we also knew that this warm hot gas that we now saw in absorption also did emit. And this is the map from the Rose All Sky survey at 3 quarter keV. But we didn't know at that time what this diffuse emission is from, okay? Rosa didn't have the resolution to separate out various components that made this diffuse background. This was later changed. Now with XMM, very good work was done. Oh, my lower part of my slide is not showing up with this, with the citation there. But anyway, Robin Shelton and her group did great work in actually isolating the signal of that is coming from the CGM. So until I got my hands dirty in this game, I had no idea how difficult this is. Okay, it is the very, very faint diffuse background with all kinds of foreground and background components. Foreground coming from solar wind charge exchange. And I'm like, huh? I'm an extragalactic astronomer. I don't know anything about the solar wind. But you know, as you go along, you're just learning these are main contaminant to the signal that you're looking for. There is the local bubble. And so, notwithstanding the cliche, it's really picking nearly in a haystack. But so you had to do very careful work in this game. And that was done by Robin Shelter's group. And so we knew that there is actually emission coming from oxygen 7 and 8, emission lines from the halo of our galaxy, as they were calling. Maybe the word CGM wasn't even coined then, possibly. So they were just calling it from the halo of our galaxy. So, just again to remind you, this emission studies, the parameter that we measure is called the emission measure. Again, very creative. And that depends on the square of the density and the path length of the gas. And again, absorption studies, you have measured column density, which depends on the density and the path length. So now finally, you have two equations, two unknowns, you can solve them, and you can get actually the physical properties of the gas that we are looking at, and that's what we thought we should do. So we really looked at lots and lots of sight lines observed with Chandra and looked at oxygen 7 and 8 absorption from there, compared that with the work that Robin Shelter's group had done, which was on emission. And finally, we could actually understand the gaseous component, which we now call the CGM, as to what its properties are. We could really show that it is really very diffuse, of the order of 10 to the minus 4 particles per centimeter cubed, really very diffuse, as you would have expected. It's truly, of course, definitely hot. We can measure the temperature precisely by looking at oxygen 7 to 8 ratio. It's truly extended, at least to beyond 100 kiloparsec. And so if you then assume it's spherically symmetric and it has the covering fraction that we measured based on our observation, its mass is at least several times 10 to the power 10 solar masses, which is at least as much as the entire disk of the galaxy, okay? So it's very massive. Now, the question then that time we still cared about is that, are the missing baryons all in the CGM? And maybe, because the Milky Way mass itself is uncertain to a factor of 2. So based on what you want to assume as the Milky Way mass, then maybe all of them are within the virial radius, so maybe not. But huge amount of mass still exists in this previously unknown component of the galaxy, which is the circumgalactic medium. So that's the takeaway here, and this is from the Chandra press office, is this is what we figured out, that if this is the stellar disk and these are the Magellanic clouds, then the entire halo of our galaxy is filled with this tenuous, warm, hot gas, and total mass is huge. Okay, so that's the takeaway here. And so then over the next few years, we were like, okay, fine, missing baryons are mostly there. Maybe some are not, some have gone off into intergalactic medium. Now let's try to focus our attention elsewhere as to what we can understand about, galaxy formation, feedback. Let's think about those things. So that's where the attention was focused. And then I'm going to move 5 more years forward and now bring you to this amazing spectrum now, not Chandra, but this is with XMM-Newton. Very high signal to noise spectrum, one of the best ones we have. It was observed for a long time, the background source, and the idea was to look for the elusive intergalactic medium. But I was like, okay, we will do that. But what I am going to look at personally is this redshift zero absorption that we know, there is no ambiguity there. And sure enough, we see oxygen 7 absorption line here, right? You see also some oxygen 8. But this is where the fun is. What we also saw here is neon 9. Okay, you expect that from the warm hot gas. But this is where the fun is. We saw neon 10. I looked at this spectrum and you want to do a jump up and down, right? Because you know that you have made a discovery just looking at the spectrum, because you know that neon 10 can't really come from million-degree gas. It has to be hotter for you to have a detectable neon 10. Then you look at the spectrum again, and you want to start jumping up and down once again. And that's because you realize that the strength of my neon 10 absorption is more, if at least as much as that of oxygen 7. But neon is not as abundant as oxygen. So you again realize that you have made yet another discovery that there are non-solar abundance ratios. But I can't really publish my picture jumping up and down, so a lot of work needs to be done. And this is where, again, Sanskriti was already working with me at that time, did fantastic work about modeling the spectrum that's shown here. The dashed blue lines is for the million-degree gas. The solid green line is for the 10 million-degree gas. And, as you expect, you see the oxygen 7 line is fitted with the million-degree gas, as you expect. On the other hand, neon 10, the million-degree gas has no contribution, and you absolutely need the 10 million-degree gas here. And in between, for neon 9, there is contribution from both. The oxygen 8, there is contribution for both, and so on. So this, of course, is our first result. And I don't know why I can't move this away. Hang on. But as I said, the same spectrum had other results waiting for us, and that's what we have in this slide, that we clearly have non-solar mixture of neon to oxygen. Again, here, the blue line is for the solar value, and the yellow line is for the non-solar value. It is neon 10. If neon to oxygen ratio was solar, we would have had teeny weeny absorption as shown here. We have strong absorption once again, again showing you the non-solar abundance mixture. And then actually there was third result that came from this absolutely incredible spectrum, which I couldn't see with my eyes because you will see why, because of what. This result is about seeing actually alpha enhancement, that if neon to iron was solar, okay, in this hot component, we would have seen strong lines of iron, which we did not see. So non-detection of iron is actually telling you that neon to iron is supersolar, okay? So this advancement is also again showing in here. So what is it telling us? Is it telling us that the alpha enhancement telling me that our contribution from core collapse supernovae, is this the star formation induced feedback that we were thinking about? And is the supersolar nitrogen to oxygen ratio telling me about contribution from AGB stars? I'm not sure whether the results are actually telling us about nucleosynthetic yields though, because there are other possibilities such as, for example, inhomogeneous mixing. So maybe it is possible that your local abundances are not the global abundances, right? So if the CGM is not very well mixed. It is also possible that oxygen is an efficient cooler, so that is, it has kind of come down more preferentially to lower temperature systems, and therefore neon to oxygen ratio is what it is. Or there could be possibly some depletion of oxygen onto dust grains even before it left the interstellar medium. All these different possibilities, these are the kind of questions that we do need to answer as we move on. But it was a lot of fun looking into these data and writing these papers. So we know the next question we wanted to know is, where is this very hot gas, the 10 million degree gas, coming from? We looked at different possibilities. There is supernova remnant along the sightline. Is it some excess contribution from local bubble? This sightline actually went close to the North Polar Spur, which is near the Fermi bubble. And we could rule out, I won't go into the details of each one, but we could rule these out. And so it does look like maybe this hot gas is coming from a little bit more extended regions somewhere. Is it really the volume feeling like the million degree gas? We do not know. Finding out where this 10 million degree gas lies is going to keep me busy for many years to come, and I'll be talking about it in just more in just a minute. Okay, so now we had seen this in absorption, but remember, by combining absorption and emission measure, we could actually figure out where things are coming from, right? So let's do it for this sightline. Look at the emission spectrum around the absorption sightline and see whether we can solve for the densities and path lengths. So we did that, but the result was, again, a big surprise. What we found that the temperature, as we detected in emission, was not the same as that detected in absorption, even though even in emission, we did see the two components, one warm hot and one hot. The temperatures were not necessarily the same. Over here, maybe they are within 3 sigma, then you can figure out, well, if they are, what that means. All that we discuss in the paper. But the point is, you're already coming closer to what I'm going to conclude in a bit, that the CGM is really multi-phase. You really do have a range of temperatures, and we are probing different things when we are looking at different kinds of absorption and emission. And this is where we are evolving toward in this understanding. So this is now the press release from ESA, because this data were from XMM-Newton. And so, you know, in about 5-6 years or something, we went from here to here. Now, not just one temperature gas, but multi-temperature gas with different kinds of abundance ratios. Okay. But this sightline that we just talked about, just okay, one sightline. You know, we can't really talk about properties of CGM just based on one sightline. So one of the things that, of course, we are pushing is to really look at the ubiquity of this hot gas. Okay, so this is another sightline that we had looked at. And here, again, we kept seeing, in addition to the million degree gas and in addition to the 10 million degree gas, we clearly see even cooler 3 times 10 to the power 5 degree gas. Okay, this is the temperature range typically seen in UV with oxygen 6. Okay, but here with carbon 5, carbon 6, we actually could go down to as lower temperature as few times 10 to the power 5 degrees. So like I was saying, yes, the hot gas exists, different temperature regions exist, and okay, this is again missing here, but you know, we are really seeing not just the the hotter supervirial temperature gas, but cooler subvirial temperature gas. And like I said, we are looking at it at multiple sidelines, trying to see the ubiquity of the properties that we actually discovered previously. And here again, we did see non-solar abundance ratios. The lines here would have been stronger if they were solar. So non-detection is actually important in here. Then again, in this cyclage, we went to look for emission. And here are a few surprises that we found. Yes, again, we found virial and supervirial temperatures. That is now really looking more and more like it is kind of ubiquitous, especially in emission, where we could see the whole sky, okay, with Suzaku data. And I might be showing that in the end. But we also saw very surprisingly that there are variations on scales of even a degree. Okay? When you look at the whole sky, we knew that the emission measure of the whole sky is not uniform. There is, you clearly see differences on very large scale, but this is the first time we could see smaller scale, degree scale in homogeneity in the properties of the CGM. Is it because of clumpiness? Is it because of turbulence? Again, these are the kind of questions we do need to answer, and comparison with simulations would be great in here as well. And the temperature ranges, we again saw there is a big scatter in the temperature range. Okay, so this is now emission measurement. As I said, we saw both the virial temperature and supervirial temperature gas in emission. And these gray bands here is the temperature where we had seen absorption. And once again, that we see the temperature as seen in the absorption is different from that in emission. Okay, and so we couldn't really just combine the measurements and determine where the hot gas is coming from. And then the question is, why is it that we don't see this temperature gas in absorption or this temperature gas in emission? That's an obvious question you need to answer. This you can easily explain because emissivity of oxygen peaks here. Okay, so that's great, that's fine. You can explain why is the emission here is because of the emissivity. Why don't we see absorption here? Maybe because it's denser gas but lower column density gas. This you can understand. This we could not explain why this is happening. Yes, we don't see absorption here because column density of neon 10 will be low. But why is it that we are not seeing emission here? To try and understand that, I think, again, from student Joy Bhattacharya did very good work here of chemical tagging. What we really did is figured out how each element is emitting at the temperatures of interest, how it is emitting over the entire spectrum that we are looking at, right? And so we can then figure out as to what is giving rise to the hot emission that we are seeing. And what we see here, and that's what is shown with all these curves over here, is the column density times emissivity. So it's like some figure of merit. We figured it out here. That's plotted here. And what you can see, these are the temperature ranges at different sightlines around the absorption sightline that we had looked at. We are actually looking at L-shell transitions of different ionization states of iron. And so there is one important thing here. We are seeing iron in emission. We are not seeing iron in absorption. Yes, I know I have work cut out for many years to come to figure this out as to why it is happening. But we can now answer the question as to why didn't we see emission at absorption sightline? Because by the time we are in this temperature range, the emissivity is really gone down significantly. And so, okay, finally, at least we understand this figure good, but this chemical tagging was a very new thing that, that was presented in this paper. Okay, so basically what we are seeing is that the hot component appears to be ubiquitous. There are reasons to believe that at least observationally there are non-solar abundance ratios. There are some possibilities that there is some kind of observationally alpha enhancement. So these kinds of observations, these now look more and more ubiquitous, though we are pushing on those fronts, that more and more we are seeing that these observations have potential to provide insights on the thermal history and the chemical enrichment of the circumgalactic medium as to how exactly the disk and the CGM are interacting with each other. But of course, as we kept mentioning, we do need to look at how what are the properties in terms of the density and temperature distributions everywhere, ubiquity of all these parameters, and then compare maybe with simulations. So, whether the anisotropy we see is due to clumpiness or patchiness or turbulence, these are all kinds of questions that we need to ask. For example, what is the distribution of different phases of the CGM? Okay, so if you HaloSat data, by the way, confirmed results of that you need at least 2 temperatures, and they had modeled hot gas as extraplanar region around the disk of the galaxy. Is that the thing? And then is the gas emitting in the warm hot phase around it and the absorption gas around it? Is the kind of picture of the CGM data suggesting, or is it showing that actually the emitting gas is the denser, clumpier gas and absorbing gas is the tenuous volume filling gas around it with some structure of hot and warm hot phases? So basically, we have warm hot in absorption, warm hot in emission, hot in absorption, hot in emission. What is the interplay of all these different phases is what we will be figuring out in a few years to come. That's the hope, at least. So that's where we are in terms of understanding our Milky Way CGM. But what about other galaxies, right? So the work that's been done until now to look for the CGM of other galaxies has been on very massive system for obvious reasons. The more mass you have, more gas you have, easier it is to detect. But a Milky Way type galaxy had never been detected as an external galaxy in emission, okay? But we did look very carefully about the parameters of what is the ideal target. We want to look at Milky Way type galaxy, external galaxy in emission. And this is what we thought that, what we should be actually looking at is this galaxy in GC 3221. And we were super excited. This is again Suzaku data. We detected the CGM of this galaxy for the first time, and L-star galaxy, external galaxy CGM detection. So as I said, this was discovered with Suzaku. If we really integrate our density profile, it could in principle account for all these missing baryons. Then we actually observed it also with XMM-Newton, and it confirmed the Suzaku detection. But the XMM data showed us something even more interesting that we hadn't seen before, that we could now actually measure temperatures in at least 4 different radial bins around the center of the galaxy. Okay, these are not great data at all, but it is clearly said, it is clearly telling us that it's very unlikely that the gas is actually isothermal. Okay, so that is what one of the first results showing that the CGM is actually not isothermal on large scales. That's what we are averaging out here, not the small clumps that we are talking about. So fine, if it is not isothermal, fine, let's try and fit it with some different profile, not a straight line of temperature. This particular profile, which is called the Maller and Bullock profile, is for temperature and densities for hot adiabatic gas in hydrostatic equilibrium in the dark matter potential well, which can be defined as NFW, then you get this kind of profiles for temperature and density. So we try to do that. Yes, we can fit the data with Maller and Bullock profile. We can get some reasonable values for temperature and the core radius and the virial radius. These are all reasonable values, but of course we don't have great constraints at all because the data quality is not good, and the parameters can go all over the place. But it would be super cool to confirm this result and really look at the profiles and density and temperature in an external galaxy, which we can't do sitting in our own Milky Way. You have to have an external galaxy to look at the radial profiles. So this would be a very interesting thing to do. And in fact, we do actually have now new deep XMM-Newton observations that are approved, and we are waiting to get those data. It's not yet observed, but it has been approved to be observed. So this would be very interesting observation to do indeed. Okay, so this is actually seeing external galaxy emission. But what about seeing external galaxies in absorption? This experiment is done a lot in the UV, right? You keep seeing O6 absorption line, carbon-4 absorption lines, silicon lines all over the place from external galaxies. That's because UV astronomy, UV spectroscopy is significantly easier than doing it in the X-ray band. But you do need to do it in X-ray band because this is what the CGME is hot, You are actually really looking at very small parameter space. We are actually looking in UV. You don't want to look for needle under the light. You want to look for needle where the needle is, and that's in the X-ray band. So, you do want to do that experiment. But your bright X-ray quasars are not fortuitously aligned with CGM of some galaxies, so it becomes very hard. But we actually thought about how to do this experiment, and we realized we can use some proxy for some galaxy where we could actually know a priori what the redshift is. And you can have an anchor. So you don't have to do the blind search of absorption, and then you have to pay a huge statistical penalty. Even if you see a 3 sigma line, nobody is going to believe it. But if you know the redshift of the line a priori, even 3 sigma is a good result, okay? So with that, we need an anchor. So O6 is a reasonable anchor, and a broad O6 is even a better anchor. What is a broad O6? Typically, you see oxygen 6 at few times 10 to the power 5 Kelvin. But if actually it is in hot gas, then the line would get thermally broadened. And so there are such broad O6 system, and that's what I looked at, and we didn't really get great, like just about like 2.5 sigma. I very clearly say in the paper, we have suggestive evidence that maybe this is there, the hot CGM, but not quite. But then here we see it very, very clearly. Another sightline. This paper I just submitted exactly a week ago, last Monday. And here now, we have a very, very clear detection of an external galaxy in oxygen 7th absorption, again, with an O6 anchor. So this has been, basically, we are having a fun ride over the last couple of decades, trying to understand the circumgalactic medium and how it is different. We discovered all these different components, and I'm not going to go over all this summary, but I want to know how much more time I have.
10 minutes
with question. Okay, so I should stop, or I can go for 5 more minutes.
Anyone have any last questions?
Well, yes. So going back to going back to the Milky Way, you indicated you expected more progress in the next few years. But the observatories you've described are all long functioning. So where is the new data going to come from?
Chandra and XMM are very much there. Suzaku is no more, alas, but Chandra and XMM are very much there.
And Chandra and XMM do much more than they've already done.
Okay, so some of the things, the data also, first of all, they're there. And secondly, we are going to look at the existing data in a different way. For example, the question, one of the questions that we want to ask is, where is the hot gas, right? Extraplanar, or is it truly CGM? And the to answer that, what we could do is look at the galactic sightlines of X-ray binaries, okay? So we look for the same kind of absorption through the disk of our galaxy, sources in the disk or a little bit off around the disk of our galaxy. And then we can model out the extraplanar component from whatever we are seeing from extragalactic sightlines to really see where it is coming from. And this is something we can easily do because we actually did this experiment before for 07 itself, for the warm hot component, because the question about even where that warm hot component come from, is it really from the interstellar medium, was always being asked. And even though we know reasons why it won't be from the interstellar medium, one being that we are really looking at a very high latitude extragalactic sightline. And secondly, we don't see any correlation with sign B, of which would have been there if it was any disk component. And the third being, anyway, but in order to answer that, even though we know that the correlations don't exist, that is more likely from the, not in the extraplanar disky structure, but truly out there, we did this experiment for 07, like looking for 07 to X-ray binary sightlines. And we took out the component and we can show that this is really truly from the extended CGM.
So
Do that again for the hot component. For example, there's one of my many projects outlined in a big ADAP proposal.
but more generally, how much prospect is there of separating out composition from thermodynamics, from temperature? Because the different phases could have different enrichment histories.
Yeah, exactly. And so, so we will keep trying. We don't know what we'll find. Whatever we have found until now has been a surprise. So I don't really know what we will find. So, but it's going to be fun. I think so. I think so. I mean, we do need to do more modeling. I mean, we have already done a lot of modeling, but we will do more modeling. We will try to look for example, also correlations with satellite streams. You know, Milky Way has other satellites coming in, like you have the Magellanic Stream. Is it something extra enrichment coming from the satellites of the Milky Way? There are many, many questions we could be asking and hopefully answering. And, you know, I have a new postdoc coming this fall, hopefully. And then, you know, we'll try to do better.
Partly a matter of getting more observing time. I don't have a sense for what the practicalities are.
So some kind of questions we can ask. Answering them is within the reach of current observatories like Chandra and XMM. Some of them we cannot answer with current generation of X-ray observatories, and I'm eagerly waiting for launch of GRISM, and we'll do better with that for sure. But it will be launched this year. So, you know, I mean, successfully launched this year, fingers crossed. So, yeah, so we have lot of, you know, I'm not worried about getting bored. I mean, there's so much to do.
Question? If not, I think we can go on for the last 5 minutes.
Okay, great. So here is something which came as a complete surprise to us. Okay, so we all know what a Rosetta bubbles are, right? So this figure is showing in red gamma ray emission, And these are the very famous Fermi bubbles, right? This, like, everybody knows what Fermi bubbles are. Now, this in blue is X-ray emission, and this part over here, that's called the North Galactic Spur. This we knew from Rosette time. If you remember my Rosette figure before, you would have thought, yeah, I know that. I've seen this before. So what did A Rosetta did? What A Rosetta found is this actually some connection plus some finding the similar emission in the southern hemisphere, making it now appear that, oh, the North Polar Spur is part of a bigger structure. And this is now what is called A Rosetta bubble, which are X-ray bubbles, which are outside of the Fermi bubbles. And this is the Pradal et al. 2020 Nature paper. We just looked at it in awe and like, wow, this is beautiful. And I never ever thought that I would actually be writing a paper on A Rosetta bubble because, you know, I was busy doing something else, right? But what we were doing is looking for the ubiquity of the hot gas. And it is, as I said, easier to do lots of cycline in emission. And because Suzaku particularly had a lot of observations all across the sky, okay? And so that's what we were looking at. So this was our Suzaku survey. We were looking at all these different sight lines. There were like over 200 sight lines that we were looking at, 200 different fields we were looking at, and you can analyze the data and see with how ubiquitous the hot gas is. That was our motivation. But as we were doing it, we realized a good many of our fields are actually around the A Rosetta bubble region, okay? So we were probing that region, doing way better spectroscopy than A Rosetta, because of course these are better data with Suzaku, and we have the regions outside, and so this is the outside rest of the external CGM against which presumably these bubbles are pushing. So we were looking at it, okay? And this is what we found, okay? This is what. Now, we did find two components in practically all sight lines. We kept saying the virial and supervirial temperature. But this is the interesting result, is that this is now the average temperature all across the sky, okay? It's practically the same. And this gray shaded area is where the A Rosetta bubble regions lie. So the temperature in here is not higher than the rest of the halo. But the emission measure, of course, is significantly higher. Of course, they are brighter structures. The rest of the halo is so faint, we had to really sweat to find it, right? The A Rosetta bubbles are shining bright. Why? Of course, because the emission measure is high. But emission measure not only depends on temperature, but also on density. And so what we are seeing, the temperature is actually the same as everywhere else. Nothing special about A Rosetta bubbles. They are bright because they are tracing denser gas. So this is actually completely different from what was the assumption made in the original Nature paper, that these are shock heated structures, okay? So what they were showing is the original Nature paper actually had this as the A Rosetta bubble shells are actually shock heated ambient gas. That was just an assumption that was made. And we actually could show that this is 100% clearly ruled out. It is not shock heated. It's not adiabatic shock at all, okay? And so the shells are bright because they're denser, not because they're hotter. They're not heated. And so what exactly is the shock structure? I don't know. I'm talking to people who understand shocks better than I do. I can't really exactly tell you whether it is snowplow or it is, some kind of so-called isothermal shock, which is basically not the adiabatic shock, but radiative shock. There are various other possibilities, or maybe we simply don't understand, but I don't necessarily know what they're telling us, but I know that what they are not. I know that they're not adiabatic shocks. Anyway, so this is what the paper I was not planning on writing, but it is now just now published in Nature Astronomy. So yeah, so that's basically what we are doing, is having a lot of fun, and we have a lot of work to do in future. I won't go over this. Yeah. Thank you again.